Hello, my name is Hugo Brument, and I will present our research work entitled Does the Control Law Matter? Characterization and Evaluation of Control Laws for Virtual Steering Navigation. This work has been done in collaboration with Anne-Hélène Olivier, Marchal, and Ferran Argelaguet. Navigation is a fundamental task that enables users to explore virtual environments. While walking remains the most ecological approach to explore virtual environments, it requires a large enough tracking area that is not always available in most VR setups. To encounter this problem, different solutions have been developed in the literature. Some techniques require physical movements of the user, such as walking in place or redirected walking, while others require minimum user motions, such as teleport-based techniques or steering-based techniques that are the ones we focused in our paper. Steering techniques enable users to control their virtual position and orientation in the virtual environment. When designing virtual steering techniques, three major components should be considered. The first one is the direction, meaning how the user can update its direction in the virtual environment. It is typically based on either body segments, such as the head, or some input device like a controller can be used as well. Second one is the input mechanism, referring to the conditions of input required by the application to determine the navigation state, such as initiating, continuing, or stopping the navigation. Last is the speed component, here they're referred as a control law, and this is the focus on our paper. Research work mostly focused on the evaluation on direction input, but not the speed component. This is why we focused our research on the control law, and this is the main scope of our paper. Control laws models how the user translation and rotation viewpoint are updated in the virtual environment considering the state of the system. It includes the current navigation state and eventual user's input. Then, transfer functions are applied to update the translation and rotation viewpoint. They take as input the state of the system and they transform it into an output like new navigation speed, acceleration, and position in the virtual environment. Rotational transfer functions are most of the time an isomorphic mapping between user rotation and virtual rotation, since altering rotation with a joystick could lead to cyber sickness. In this work, we will only focus on the translation update, and we can categorize translation transfer functions into three categories. Discrete control laws enable the user to select one navigation speed from a predefined set of speed. Continuous control laws increase control by allowing user to choose the speed over a continuous scale. Finally, adaptive control laws takes into account additional system state in order to adjust the navigation speed. For instance, Argelaguet created an adaptive control law in which the spatial relationship between the users and the virtual environment on one side and the perceived navigation speed on the other side is used to adjust the speed. In contrast, the joyman developed by Marchal et al. Modulates the tangential speed according to the actual rotational speed in order to better resemble the dynamics of real walking. Our motivations for this paper were first, to have a better understanding of human behavior during navigation in virtual environments with virtual steering techniques. Most of the research work about the evaluation of steering techniques focused on performance or spatial awareness, but the role of control on trajectories and user preferences remain unexplored. Besides, guidelines regarding the designs of control laws are not entirely clear, making reproducibility of existing models difficult or leading to poorly designed control laws. If you want more information about characterization of control law, you can check section 3 of the paper. Our research questions were, first, is there an effect of the speed update on user behavior during a navigation task in terms of the way they perform trajectories and also subjective preferences? Second, is this behavior similar for a given task involving different curvature? We wonder also if the behavior could differ if the navigation task was different. To answer these questions, we designed an experiment where the objective was to analyze spatio-temporal features of trajectories during navigation in virtual environments. We chose a slalom task as it involves curvilinear trajectories and change of directions. The slalom consisted in 12 turns with gates that participants had to cross. We designed different slalom by varying the curvatures of the turns. In the experiment, we compared three different control laws that we will describe right after. In our experiment, we had two different between-subject variables. Regarding the control law, we used three different ones. User could enable motion in the virtual environment by pressing the HTC Vive controller trigger. The direction was defined as their torso orientation. Depending on the control law, the speed was computed as follows. the constant control law has a binary behavior. Either the user was not moving, meaning not pressing the controller's trigger, or he was navigating at the maximum speed Smax, set as 1.4 meters per second. The linear transfer function took into account the continuous nature of the input data and sets the spot accordingly the controller's trigger. So the more the trigger was pressed, the faster he was navigating, reaching the maximum speed Smax. Finally, for the adaptive one, we chose a function that takes into account the relationship between the speed and the curvature of the actual trajectories in human walking. The speed was therefore updated according to the radius curvature of users, or trajectory, as a power law. You can find more detail of the implementation of this control law in the paper. We also considered the curvature type of the slalom. The slalom was defined as sinusoidal trajectories where we modified their frequencies to have either high HC, medium MC, or small SC curvature, as shown on the right picture. Participants did 3 blocks of trials, 1 per control law, and they had to do 4 trials per curvature types, resulting in 12 trials per block and 36 trials in total. Here is a video of the participants performing the slalom with the high curvature with the constant control law. At the beginning of each trial, the participants had to press the trigger to notify he was ready. Then, after a 3-second countdown, he could start performing the slalom. The green gate indicated the next door to cross. If the participants did not perform well the slalom, the trial was rejected and participants had to do the trial again. Participants had to orient their torso in order to navigate across the doors. At the end of the trial, they had to answer the following questions. How comfortable the trial was. Rate from 1, not comfortable, to 7, very comfortable. This question was here to assess how the slalom was comfortable regarding the type of the curvature and the control law. We had 18 participants without any ocular or locomotor disorder. We recorded body segments and motion data, such as the head and shoulders position and orientation. We collected subjective measures between blocks, such as SSQ questionnaires to assess cyber sickness, NASA, TLX, and use scores to assess the usability and cognitive demand of control laws. We also gathered the answers from the question at the end of each trial. We conducted 2 main analyses, one global, focusing on the trajectory performed during the entire trial, and a local considering the slalom turns. We defined the turn as the trajectory between 2 inflection points of the sinusoidal-like trajectory, as you can see on the right picture. We performed a spatial temporal analysis by computing distance achieved in the virtual environment, as well as their physical movement in the real environment, meaning their torso rotations and translation. We computed participants' linear speed, acceleration, and angular speed during each trial. To assess the effect of the temporal variable during a slalom turn, we used the SPM method, statistical parametric mapping, that allows comparing time series data of different trials, taking into account their variability at each time step. Our hypotheses for the experiments were H1, the control law and the curvature would influence the performance and the spatio-temporal parameters of the trajectories, and H2, user would report better comfort and subjective results with the adaptive control law, but also the curvature type could influence users' navigation. Regarding the results, we found that, thanks to the global analysis, that first, on the right picture, is shown the average virtual path followed by participants depending on the control law and the curvature type. We can see the great similarity regarding the path followed for a given curvature across the 3 control laws, meaning that participants performed the slalom task in terms of trajectory with the same manner regardless the control law. Now, if we look at the following table reporting the mean and standard deviations of spatio-temporal variable during a whole trial for each control law and curvature type, first, we can notice that the control law and the curvature type had an effect on most of spatio-temporal variables, and in particular the speed, acceleration, and angular speed. Adaptive control law provided lower and less variable profile than the constant and linear ones. Another interesting result is the effects of curvature type on distance achieved in real environment. It means that the trajectory curvature influenced participants' translation and rotation in the real environment, where the higher the curvature was, the higher the movements in the real environment were. Regarding the local spatio-temporal analysis, the SPM method showed an effect of the control law and an interaction effect of the control and the curvature type on angular speed profiles, but also speed and acceleration profiles. Regarding the angular speed, we reported lower angular speed profiles with the adaptive control law than the constant or linear ones. The figures show the average and standard deviation of the temporal evolution of angular speed depending on the curvature type and the control law. The high curvature on the left, the medium on the middle, and the small on the right. Each control law is represented by a color, the constant in red, the linear in blue, and the adaptive in green. We can see that the lower the curvature is, the lower the angular speed is, but also that for each curvature type, the angular speed profiles remains always the lowest for the adaptive law than the constant and the linear ones. Therefore, the global and local analysis validated our first hypothesis, H1. Regarding the subjective results, we did not report any effects of control law and SSQ and use scores. However, we reported effect on nasal-TLX scores on the effort and physical subscales, where you can notice on the box plots that the scores for the adaptive law are lower than for the constant or linear one. Regarding the question asked at the end of each trial, we found an effect of the curvature type where the smallest curvature appeared the most comfortable and the high curvature the least comfortable. But we did not find any differences between the control laws. Therefore, the results do not fully support H2, but provide interesting insight on how the control law can alter user experience while navigating. So based on the results, does the control law matter? Well, it does. For instance, it can alter participants' kinematics, where we showed that adaptive control law reduced the variability in speed and acceleration profiles, but also in angular profiles where participants' rotation were similar regardless the type of slalom. It means that the control law can influence the way participants perform the rotations during steering navigation. This kind of behavior show the interest of considering control based on human behavior. We remarked that they were rotating differently, with some participants only rotating the upper part of the body without moving the legs, or rotating their full body with the feet included. Besides, the adaptive control law results in a lower perception of effort than the constant or linear one. This could be explained by the lower angular speed profiles generated thanks to the adaptive speed update we designed. We showed the importance in the choice of the control law, but it is also important to consider that the task matters as well, where we showed that the high curvature trajectories can be uncomfortable for the users and results in higher users' movement in the real environment. Our results suggest that there are still some work to do to improve the control laws for steering techniques. First, it is important to consider all the components that a navigation task involves in order to assess them. First, locomotion, the ability to move and produce motions of the center of mass. Path integration, the ability of humans to mentally update their position and orientation using information about self-velocity and self-acceleration over time. And wayfinding, the ability of updating self-position and orientation related to the known places. In our study, we only assessed the first component, the locomotion one, and the others still need to be explored to have a better understanding of control laws. Besides, it could be also interesting to consider different metrics, such as the body behavior, user perception, in order to improve the designs of control law. Last, the lack of literature about taxonomy of control laws and especially the transfer functions prevent VR practitioners from exploring the potential of new control laws. To sum up, in our study, we assessed the effect of control laws and curvature type on spatio-temporal features during a slalom task. We recommend the use of adaptive laws for trajectories involving high curvature turns since they could improve user comfort. The objective of our study was to improve steering navigation in VR. With the characterization, we aim reproducibility and guidelines about the design of control laws. And with the experiment, we aimed results to understand benefits of adaptive control laws on user navigation. In future works, we should assess these laws in tasks that better represent ecological situations with less constrained trajectories and more realistic tasks, but we should also evaluate and assess control laws at the individual level since we noticed high intra-subject variabilities. Thank you for your attention, and now I'm ready to answer to your questions now.